All right, so apologies on the technical issues. I'll have to figure out what it is that my computer decided to turn off. But let's get going with the class. You will notice that I have, or maybe you notice, maybe you don't. I'm gonna open it right now just in case you didn't. So I have graded the exam, and I have posted a solution in the folder on Canvas, and I'm going to open that solution quickly and comment on the grading. So one thing that you can see on Canvas, what is your grade? There is a total of 70 points. Does everybody see this?
Yeah.
Okay. So there's total of 70 points. And I have, I'm right now scanning your graded exam. So you will individually, and then I'll email you. So I'm halfway through. It's a bit of a slow process. Let's say that my scanner at home is nowhere near in speed to what I normally use at the at UT-PGE, but oh well, I don't have access to those. So I'm gonna, by the end of the day, you will get an email with the scanned solution that you can compare with this solution key. And then we will, I will be available during office hours, but I'm thinking I can just separately organize, or we can just organize the sessions that you can sign up to kind of review your exam via a Zoom meeting separately outside of the regular office hours. So that we don't overwhelm office hours with individual review. So let me just quickly go over the solution. So there was 70 points. The first problem was dimensional analysis, 25 points, and basically the time t taken for the temperature of the sphere center to reach a given temperature, critical temperature Tc, is a function of a number of variables. So there's the diameter, thermal conductivity, density of the sphere, specific heat capacity, temperature of the Ts of the fluid surrounding the sphere. So basically what we are looking for is the functional relationship. T is function of diameter, thermal conductivity, density, heat capacity, and temperature Ts. So after that, you need to know the dimensions of these. So there was a couple of times, on a couple of occasions, the mistake was to actually put TC here. TC is given, so it's actually not, strictly speaking, is not a variable in this problem. Though if you put it in the set of variables, that's actually just fine. But basically the time, or delta T, is what we are really looking for, but I named it T, so I was sticking with T, but it's really delta T. And then I can assume this as a power law model, so all of these individual things have power, and basically then it's all about knowing the dimensions of everything. A common mistake was to keep energy as joule, and also write an equation for it. That's not correct, because joule can be expressed in terms of mass, length, and time. So it can be expressed in terms of more fundamental units. And a few people forgot or did not properly include temperature, which I'm referring to here as units of temperature as theta. You can also relate this as kilograms, meters, and so forth. That's just fine. But this is, I'm sticking to the notation from the class. And then after that, basically I have a unit of time on the left-hand side, and all of these variable units on the right-hand side. So I have to make sure that my dimensions match. So for time, I have on the left-hand side, I have 1. And on the right-hand side, I have, where is it? Minus 3b and minus 2d. So that gives me the first equation. And I keep doing the same for all the others. I have 4 types of independent units: time, length, mass, and temperature. And that gives me 4 equations. Since I have 5 unknowns and 4 equations, I cannot completely solve them. But once I go through the process of expressing everything in terms of one other, I have chosen B. Basically, then I will get, oh, this scan is a little bit poor, I apologize. So this was actually me experimenting with my phone as a scanner. I have here time is a to the, so basically where I don't have the dependence, so this is d to 1 minus b, this in itself does not depend on b, so I can basically pack that on the left hand side together with time. So I have this new dimensionless group that depends on this another dimensionless group to b, raised to the power of b. And one check that you can conduct once you're done with this is that this indeed is dimensionless. So you do on a side, you do a check that this is dimensionless and this is dimensionless, and that tells you whether you made any mistakes. So that is the number 1. Number 2, most of you got correct, that this is shear thinning fluid is right here. Now on the graph of tau yx versus shear rate, the effective viscosity is the slope of it. Now if I have a power law, then the slope will differ. And I had to let my other coworker, that is my dog, out of the room. So that slope for shear thinning fluid at lower shear rates is larger, and at higher shear rates is smaller. So we can see that the effective viscosity here at what I drew as a 0.8 has a larger slope than effective viscosity at B. So basically my effective viscosity is slope, and the slope here is larger than at B, which basically makes this a shear thinning behavior. The next one was basically, we were given a Newtonian fluid velocity distribution. This was, I'm looking at the cross section YZ, and basically the flow is going inside a duct that we are looking the cross section of. And I have, I pointed X in this direction. Whether you point X to the front or to the back is not all that important, but it's orthogonal to this Y and Z. So basically what we're given is the X velocity through this duct in terms of Y and Z. And I'm pretend that I know this average velocity. Now, what I asked is to derive expressions of the shear stress. So this is really an application of the formula for shear stress. So we have a formula for tau Zx and tau Yx. And when you do a little bit of derivation, then you get something like this for any Yz. So if I want to plug in at Z is equal to B, if I plug in B here, I will get 1 over B over here, and that gives me expression for the shear stress at this Z is equal to B. So Z is equal to B is right here. Okay? And I can see that my shear stress is actually changing as a function of Y. Now, as given, we drive, so this is my X direction momentum transfer across plane in Z. So basically this tau Zx points on the top of the plane in the positive, what I marked as positive X direction. So this is the basically going towards us, and it's a shearing the top plane, which I'm assuming here has some length. And then the similar thing is happening on the side. I have X direction shearing because of the X direction velocity. And this is my tau Yx on this side plane. Again, it's pointing in X direction. Now, after that, I asked for total viscous force. So for that, I have to integrate. And since my shear stress is actually changing on this side, we need to integrate per length. So you can assume that there is a length here in x direction. So you can basically integrate over some length, but or just multiply by a length, but integrate in this y direction. So if I integrate, I get this fx force. So I have the top plane b, z is equal to b. Then for z is equal to minus b, I get what I take the definition of shear stress at minus b, but I have to take it with the negative in front of it into account, essentially because when I'm on the top plane, my shear stress by definition is momentum transfer from this lower z values to higher z values. And since z is the z is equal to b plane is in this higher value, then tau zx gives me precisely what I need. And that is the viscous force exerted by the fluid onto the solid. On the bottom plane, since technically what tau zx is giving me on the bottom plane is what solid is exerting on the fluid, so I just have to take a negative of that. But it's really the same values because of the problem is symmetric. This is really this negative, this is the same as this. And then I have a similar thing happening on this side, okay? So, so A and minus A, and then it's just a calculation and integrating this, this portion is what needs, this portion is what needs integrating with respect to Y, and this portion is integrating with respect to Z. And then I get my totals, which is just the calculus from that point on. Okay, and then final problem is a Newtonian fluid of viscosity mu flowing up on the outside of the cylinder. Apologies for a poor scan. I might need to rescan this. So basically there is a solid and that has radius r, so solid cylinder, and my fluid is flowing downwards on the outside of it. So at radius r0, so I'm assuming this fluid layer has a slightly larger radius r0. So what I'm assuming in this problem is that my velocity is a function only of the radius, and my radial, so I have only z direction velocity going down. I'm driven only by gravity, and there's no other pressure gradient applied. I'm basically open to atmosphere here and here. So my P0 and PL, if you will, are 0. And the only pressure gradient is rho gz. So I have that generalized pressure and only a rho gz term in it. Now, Vz is a function of r by assumption. And r is, so Vr in itself is 0. So there's nothing going in radial direction. V theta is 0, so there is nothing rotating in theta direction. And I'm assuming boundary conditions, no slip on the solid wall here. V is on the wall uppercase R. I have a 0 velocity, and my shear stress, and that is here where my basically fluid or liquid is in contact with atmosphere or air. I'm assuming that shear stress is 0. Okay, and again, my pressure drop is only hydrostatic pressure. So I have chosen, I gave you an option to derive the differential equation for shear stress, or use shell balances or equation for motion, whatever it is that you would like. And basically, I chose here to just use Appendix B5. That's the appendix that actually has all components expressed in terms of shear stress, which is what we need. Or you use the velocity one, but you recognize what shear stress is in there, and then solve for it, because that's what we need to solve for, and that's what our boundary conditions are. So basically, when I kill all of the terms that are derivative with respect to time, or they have v theta in there and vr in there that are both 0. then basically what's left is this equation. My dPdZ is also 0 because I'm open to atmosphere at both ends, and those boundary conditions are the same. So the only thing that is left is really that 0 is minus 1 over r ddr r tau rz plus rho g. This gz in this particular coordinate system, gz is equal to gravity. If I oriented this z direction upwards, then it would be minus g. So that's just a matter of how I'm orienting the system. Excellent. So then we can integrate this to get tau rz. One big difference from how we solved some of the problems in class is here, this is my general tau rz, and it's divided here by r. I cannot assume that C1 is 0. Why? Because the problematic radius is equal to 0 is not in my domain. Radius is in the middle of the solid here. There's no fluid there, so there's no problem with it either. So I cannot just say, oh, this C1 is equal to 0 because this might blow up. It's not gonna blow up, not in this geometry. So basically it remains there, and I have to apply my boundary condition that shear stress is 0 at the R0. That gives me tau RZ. And then I asked just to set up the equation for velocity. So basically my minus mu dvzdr is equal to the expression of tau RZ I had. And the boundary condition I need to actually solve that is Vz of R. And I didn't ask for solutions, so that basically is it. All right. Again, so I will probably within shortly after office hours or this class, I'm going to complete scanning and email you individually your graded exam, and then we can set the time to discuss. But please look at these problems first. Any questions? I'm gonna take silence as no questions. Okay. All right, so we will move on, and we will actually start a new lecture today. I was originally planning to discuss the concept of shear friction factors, which essentially enable us. So all of the oh, there's somebody asking a question. Average on the exam. Average on the exam was 48 out of 70. Oops. Out of 70, which is equivalent to about 68%, approximately 68%, which is a little lower. I normally try to shoot for or would like to see about 72 to 75% as an average. So it's a little lower, but this class is also a little more difficult than 310, I would say. I don't know what you would say. Yeah, and then the minimum on the exam was 31, and maximum was 63. So 63 is 90% essentially. Okay, any other questions? Yeah, go ahead. Any other questions? You can unmute yourself and ask questions or do a chat. Okay. Okay. So what I originally planned is to do friction factors. However, we are a little short on time because I don't need to tell you why. So we're gonna move on, and I'm just gonna comment that all of the equations that we have so far looked into, they're dealing with laminar flow. So there is no, the only flow type that we have learned how to solve is slow flow, where I don't have all of my fluid is behaving in an orderly fashion. This is not always the case. And with what we normally evaluate, we evaluate that with Reynolds number. So at high Reynolds number, I have turbulent flow. So none of the equations then don't necessarily apply. That is typically measured and correlated through experiments. And there's a concept called friction factor, which is essentially a factor that tells you how you should multiply your overall flux, give or take, to basically get the correct version for turbulent flow. So we're not going to go into that lecture. It was supposed to be relatively short, but it does have associated problems that would probably take at least 2 class periods, if not more. So I'm gonna this is where I'm going to be shortening planned material. I will post a lecture on it for those of you who are interested. So basically, it's going to be an optional lecture posted later. But I will move on now to heat transfer. So we actually have a new lecture that we are starting today, and that is the heat transport. And we will go through similar motions of also working through shell balances when solving the problems, but you will have an option of also just applying the formulas. So let's get going. Let's briefly introduce. So basically heat transport, the related reading will be in chapter 9 and 10. Chapter 9 is more about just defining what we call is thermal conductivity of materials, so material properties, and going over them. And chapter 10 is really about shell balances and solving problems. So just if we think about the cause of energy transport is the thermal gradient. Let me just move this a little up. Okay. Thermal gradient. So if I think about subsurface, there's about 25 Celsius degrees per kilometer of difference. So if at 1 kilometer of depth, come on, at 1 kilometer of depth, the temperature is 25 Celsius degree warmer than it is on the surface. So here in Texas, what's the temperature today? 15, 20 Celsius degrees maybe? Can somebody check quickly online? And then report via chat. So whatever it is at 1 kilometer depth from the surface, wherever you are, is basically 25 Celsius degrees more. So somebody checked. 21 degrees. Yes, that's pretty low for Texas. So of course in summer it's about 42 Celsius degrees, but right now it's 21 and it's pleasant. So at 1 kilometer depth, it is 46 Celsius degrees right now. As I move down, it warms up. So of course, most of our reservoirs are actually below 3 kilometers of depth. So you can see that that temperature easily goes to rather high for any reservoir of interest. Now, and this is away from the tectonic boundaries. Near tectonic boundaries or boundaries, the plate boundaries on the surface of the Earth, there might be more exposure to the molten rock below. So that might actually cause a higher temperature. So that rock, partially molten rock, is at the temperatures, it's molten rock, so temperatures are typically 700 Celsius degrees and higher. And it's basically, this molten rock is postulated, nobody checked, nobody put their finger in there, but it's postulated to exist everywhere beneath the Earth surface. And you can see here crust, upper mantle, mantle, outer core, and so forth. The temperature of the Earth's inner core is estimated to be basically in 5,000 Celsius degrees and above. Now, mean heat, I actually have it stated in Kelvin here. Oh, wow. So that's just a shift, but it's still in thousands of Celsius degrees. Now, mean heat flow, so because of that difference in temperature, there's a heat flow over this continental crust, and it's a little different for where we actually have continent and where we have the ocean, basically because the heat transfers differently across land mass and ocean. Now, we are actually interested in applications in petroleum engineering. So here's how thermal gradients look like in a petroleum application scale. So this is, I picked this from a journal where I basically found that it has a nice shown measurement of thermal gradients. I have to measure temperature in a number of wells, and then after that you can basically extract or interpolate a smooth map like the one that you're seeing here. And what you're seeing here is geothermal gradient contour map. So if I walk on, for instance, this contour, this is along this contour is where the gradient is 4 degrees Celsius per 100 meters. Okay, and this is estimated from well logs. Now, oil can form at we know that oil forms at shallower depths, and if my geothermal gradient is higher, so I will have a maturation helped by a higher geothermal gradient. In petroleum engineering operations, there are also, so this is basically just what is there. However, the petroleum engineering operations can locally be a source of thermal gradients. So if I inject at, we were saying at 3 kilometers of depth, my temperature will be 25 times 3 plus whatever I have on the surface. So it's gonna be very high compared to whatever drilling mud I'm circulating in the well. So drilling mud, fracking fluids are typically cooler than whatever formation I'm injecting them in. In steam injection, if you go to Canada, and there's a lot of stimulation essentially to warm up relatively shallow formations, then in steam injection you actually have an opposite problem where you actually injecting something that is way hotter. So in that sense, petroleum engineering operations are often source of thermal gradients. So what are the mechanisms for energy transfer? Let's first recall, just briefly review what happens with momentum. What we realize is that we have a change in momentum, and we can have what we were calling molecular, this is my combined momentum transfer, and we can have basically the pressure gradient driving it. We can have external forces such as rho g here, and then we have viscous forces as well as convection. So this portion was, if you remember, things that kind of basically the packet of fluid that moves into my control volume, and there's a change in momentum associated with it, which is, this is where it's measured. Gradient of pressure can change momentum, and then also the friction between different layers of fluid, so this was the viscous term. So those are the, basically I have convective, molecular, and external forces. Now, more generally, I always have flux, and that could be momentum, energy, and mass. If I impose gradient of potential that can drive the motion. So in case of momentum transfer, that gradient of potential was differences in velocity. In heat transfer, I'm going to have differences in temperature. So basically differences in temperature will drive the motion. Presence of fluid will complicate things, however, because yes, again, I will have convection and things can actually move into my control domain, as well as just transfer by contact. Okay? Now, we had a very simple relationship that defines shear stresses for momentum, which was essentially linear for Newtonian fluids. So there is this is the gradient I'm talking about. And here I'm just looking at one of the velocities, but we know for velocity field, gradients are essentially all of the gradients you need a tensor to express. So as a result, we had shear stresses that were expressed as a tensor. In terms of energy, this is going to be a little simpler because temperature is just a scalar field. So I have a gradient of temperature, and that's a vector in itself, a vector field, but everything is described by vector fields, and I don't need tensors anymore. So that's the good news. Okay, so I will also have molecular transport mechanism for energy, and basically molecular motion is underlining that one. We will have convective energy transport, things that are simply brought into my control volume. That's specifically when I have bulk motion of the fluid. So what this really results in is that we need to know what are what is my velocity distribution for the fluid in order to take this into account, which is why we discussed momentum balances first. And then we're not gonna go into diffusive, where I actually have interdiffusing of different mixtures that could have potentially different temperatures, because this would involve mass transport, which we haven't covered with. And we're not gonna go into radiation. I don't think that we will have the time. So radiation happens when there's basically no material medium required for the transport of energy. Now, basic law for heat conduction that is basically equivalent to Newton law is going to be Fourier's law. Okay, so we're gonna, instead of my motion between or fluid between two parallel plates, I'm going to have, in the simplest case, just a solid material. So that simplifies there's no bulk motion, there's no convection. And in all of the heat transport problems, that's the type of problem we like solving because it's way simpler to solve. So let's start with that. If I just have a piece of homogeneous material, and I have area on top, which is A, I have the thickness of this material, or the separation of top and bottom plane, which is Y. Then let's say that initially I have top and bottom areas at temperature T0. So if I have them at the same temperature, then there will be no heat transfer. Now at time T is equal to 0, I will raise temperature of the bottom plate to T1, which is presumably higher than T0, and wait. Okay. So after some time, so initially I'm going to have higher temperature here, and because of the energy transfer in this cross direction, eventually most of my plate will, most of this thickness will heat up, assuming that I keep this temperature at the bottom. I have a heater that is keeping it at T1. Eventually, I will actually have this linear profile that basically goes from temperature T1 on the bottom to temperature T0 on the top. Okay. This I think is something that is familiar. Basically, I don't know how many of you are holding a cup of warm coffee at this hour, but basically if your coffee is warm, then it's warming up the walls of your cup and eventually your hand. And if you let it go on, it's going to equilibrate. It's also, of course, there will be a transfer to the air as well. So it's a little more complex problem than this little plate. But this is the type of equilibration of temperature that is happening pretty much all the time in your everyday life. So the simplest model for this transfer is to look at the heat flux per area. Fluxes we typically normalize by area. And it's assumed that it's proportional to the difference in the temperature. So delta T, which is in this case T0 minus T1 or T1 minus T0. And it's inversely proportional to this plate separation. And the coefficient for this simple linear model that is required for this to work is called thermal conductivity. One of my coworkers is trying to get into the room. All right, so please disregard the background noise. Now, in this case, if I put a coordinate system, okay, then this will be my presumed y direction, similar to our parallel plates for Newtonian fluid. Then in this case, I'm going to normalize this as small letter q, flux, so normalized linearized heat flux, which is per area. And so basically qy is then negative k times dt dy, where this is a derivative. This is just now in one direction. So this is basically when I take this limit as the separation goes, y goes to 0. Why is a minus here? Why do I have a minus? Anyone? Wake up time. Grab that cup of coffee. It is flux out. What do you mean by flux out? What is the direction of the flux?
Is it because the heat's flowing from the lower to the higher like levels?
Well, okay, lower and higher, you mean in the coordinate system?
Yes.
So yes, so technically yes, our coordinate systems always point from lower to higher. That's what I consider positive in any coordinate system. And I write down a positive number, right? If this was, I don't know, 0, 2 times the identity vector in y direction, that 2 means I'm pointing from lower to higher values of y, right? As a positive number. However, when I'm flowing physically, I'm going to flow from higher temperature to lower, so opposite that. And that's essentially what's captured by a minus. Okay? So if my temperature on the bottom has to be higher than on the top, so it has to be sort of in the opposite direction of this coordinate direction for me to actually flow in the coordinate direction, right? And that's what's captured by a minus. Excellent. So great thing is that if we have what we call isotropic, iso means the same, tropic refers to same in every direction. So if I have my medium or my material that is homogeneous and it has properties that are similar in all directions, then K basically describes this thermal conductivity is just constant everywhere. So I'm going to happen, this is what we just now derived, and we're going to happen, everything will happen in all directions just the same. So Qx is minus K dt dx, Qy is minus K dt dy, Qz is minus K dt dz. So this is essentially a vector equation. So I have that my vector Q, these are components, Qx, Qy, Qz, is minus K gradient of T. Okay? So these are gradient components, and K is constant. Does everybody see how I got from here to here? If not, stop me now. Okay, so this equation is way simpler than what we had for momentum transfer, because again, my temperature is scalar field. So it's way easier to look at the changes in the scalar field than it is. I don't have to go across different planes and different velocity components and so forth. This is what's simplified. What's going to be complex is that if I do have fluid flowing, I first have to know how to solve for fluid motion and then incorporate how that basically couples with the changes in heat transfer. Okay? In some sort of anisotropic case, this K would be different across different planes in different directions and essentially described by a tensor. And in which case I would have that tensor multiply gradient of T. So this is again not so commonly used in applications, or we simplify our solution to the layers where things are homogeneous. However, there are media in porous media that are anisotropic by default. So if clays are one of those. Clays typically have platelets that when they align, then basically they create barriers in the transfer direction to the plate that have to the plates that have aligned, and there are different types of transfer along or across those little plates. Now, thermal conductivity units, we actually just had them mentioned in that exam, but they were given, are basically of energy per time per area, and then times length per temperature. And you can actually figure that out from here, right? So this is temperature per length. When I put that on the other side, I get this term. So this is power, joule over second is watt. So this is power unit per length per temperature, okay? There's also thermal diffusivity, is what I get when I normalize this thermal conductivity by density of the material and Cp and the heat capacity at constant pressure. Okay? So now I will briefly mention convective transport of energy. And then we will basically stop for today and continue next time. So basically, when I have a control volume and there's fluid motion, there's a problem caused by basically my volume, my control volume, or my equations being expressed with respect to this position here. But as the fluid moves, the fluid that position is seeing differs. So there's stuff that is simply flowing into my fluid. So if the fluid that moves in is at a different temperature, well, then my temperature changes simply because of the convection of that fluid. So we need to look at the kinetic energy per unit volume, that is 1/2 rho v squared. And internal energy, so the total energy that is carried in has different components. So the fluid itself has the kinetic energy as well as its own internal energy that is summation of all the others that could possibly be in there. And we are using this little U hat as for normalized internal energy. So basically, rate of energy per unit area that is carried across this X direction is, this is energy of that fluid packet evaluated at the side crossing, and it's crossing with this velocity. It's crossing this side right here, right? So basically, this is what's carried in, orthogonal to the X direction, and I could go around all of the directions and evaluate it the same, and I have to also do the same for all of the sides. And with respect to this coordinate system, we're going to look at this lower side X. That's what's carried across is in, and this upper side of the X at X plus delta X. If you remember the shell balances, this is going to be what's carried out. And the same actually goes on in all other directions. So I'm going to have the similar thing happen for the Y direction and Z direction. So my convective energy flux vector is basically, this is the energy of the fluid packet, and this is the velocity with which it moves into my fluid element. So this is my convective energy flux vector. And again, good news is we have vectors describing this and not tensors anymore. This is the equivalent of what used to be rho VV tensor in momentum transfer. Now, if I just had any general surface, this is a coordinate system. So I'm looking at the cross coordinate planes. In any general case, I would basically do a projection of this vector to the normal to the surface and multiply it by area to look at the rate of convective energy transfer across that general surface. I'm going to stop here because I'm going a little bit over time because of my technical difficulties at the beginning. And we will also look into the work that basically friction of the molecular layers of fluid can introduce a heat source, and that needs to be accounted for as a work of the viscous forces. And we're going to keep or continue on that topic on Monday. Any questions? No questions? Did I put everybody to sleep successfully? It's kind of rainy outside.
It's sunny out here.
Oh, well, here it rained, in Austin it rained, and it's still kind of seeping, and I think we're gonna see rain continuously up until tomorrow or so. All right. Well, so one person is not sleeping. Everybody else.
Are you going to send out like time slots to set up a meeting after
Yes.
the exams are returned?
Yes.
Okay.
So I'm gonna probably do a Google Calendar or something like that. I think I can do calendar slots on Google Calendar. So my first thing is to finish scanning, which is a little slow on my scanner. And then I'm gonna individually send you your test, and you can compare it to the solution, and then we can discuss.
Great, thank you.
And then you can just sign up, because otherwise, if I just have these open office hours where there's no physical door, virtual doors are difficult. So I don't want to. I want everybody to have their privacy discussing the exam. Any other questions? All right. Does anybody need to stay on for the office hours, or should I just go and do my scanning and then do my scanning and then open up sign up slots? One more question also. Are you all open to meeting sometime during like tomorrow morning, since kind of we're all cooped up in the house anyway?
That's fine.
Can I have some sections tomorrow morning?
That works for me.
Okay, because that's actually kind of easier for me. Childcare is more easily available when my husband is not working in parallel.
Thank you, Professor.
All right. Well, I hope everybody is doing fine. If not, let me know if I can help in any way. And I see you on Monday in class and at some other times as we sign up for a discussion of the exam. Thank you.
Thank you.
All right. So Min, I'm gonna now go finish scanning, but I'll need to play with my computer. So I might during the day invite you for a Zoom meeting to figure out what's wrong.
Okay, sure.
Yeah, I don't know. Like, again, I did have an update. I had a Windows system update. So between that update and something got turned off. But yeah, this very moment, I didn't want to spend 15 minutes figuring out where that something is.
Yes, I think it's the access, the Zoom access to your camera stuff.
Yeah, but Bandicam has the same. I
Oh.
tried recording Bandicam, and Bandicam is ignoring my camera too.
Yes, yes. So I searched on Google a little bit before the class. It was saying that you can try other stuff to see whether they can access your camera or not. And if they can't, maybe it's the camera.
Right. So I need, yeah, some sort of, I'm sure it's a safety setting of some sort that suddenly turned on. Oh, well.
Okay.
I love how it just shows up suddenly.
Yeah.
Anyway. All righty. Thank you.
Okay, thank you.
Did anybody, you posted the homework, right?
Yes, yes.
Yeah. Did anybody already start working on it?
I don't know. Yesterday.
So nobody showed up in office hours?
No.
Yeah, so that means nobody started working on it. so send them a little reminder. By the way, I posted the homework. Don't sleep over there.
Okay, cool.
Yeah.
I will.
Okay. Thank you.
Thank you.